Okay, now we are going to see the electric field intensity due to a uniformly charged spherical shell. Okay, so now I have taken this is a spherical shell on which charges are uniformly distributed. Therefore, here this is the charge. Okay, so this is uniformly charge is uniformly distributed. Okay, now I am interested in finding out the electric field at points actually in outside the spherical shell, that is outside the spherical shell, and on the spherical shell and inside the spherical shell. I have to find out the electric field intensity at 3 points. Okay, what are they? One is outside the spherical shell, the point outside the spherical shell, point on the spherical shell, and point inside the spherical shell. Okay, so now we are going to start with what is that field outside the spherical shell. Outside the shell, so discharged shell. Okay, so for that, let us see my point. My point is here. This is the point P. Okay, so what I want is, so I have to find out the electrical intensity at P due to this spherical shell. Let R be the radius of the shell. R is the radius, and let center be O. Okay, now therefore I am and my point of interest here is at a distance, okay, R. This is, let it be, and this is R, small r. Small r is the distance of the point concerned. Okay, so now to find out the field at P, okay, what should I do? I have to apply Gauss theorem only here. Okay, therefore I need a Gaussian surface. So what should be the Gaussian surface here? The Gaussian surface here, the Gaussian surface has to be, what is that? It should enclose all the charges, and here therefore it should be a sphere. Gaussian surface may be of any shape, but in our line of charge we have taken a cylinder. Okay, and now the ideal Gaussian surface that you can take is a sphere. Okay, therefore now let me have Gaussian surface. See here, this is see, this is the Gaussian surface. Okay, so now what is that? This is the Gaussian surface. 1 second. Okay, right. Therefore, and my point of interest here is P. Okay, let me highlight it somewhere. This is the point of interest, right? Now, so what I have to do? I have to apply, what is that? The Gauss theorem, according to Gauss theorem. Okay, let me have. Theorem. Okay, what is E dot ds? Now I am going to take a very small surface here. Okay, and what is that here? Actually it is on the sphere. On the sphere means it is only partially I am able to show because it's 2D. Actually it should be a circle. That is, you have to take ds around the point of interest. Now I have showed only the partial surface here. This is the surface. Okay, therefore what is the area here? It is ds. Okay, therefore ds means what will be see here there are two things we have to see. What is the area vector? Area vector will be taken in this direction, normal to the area. And what do you say about the electric field? Electric field at this point will also be radially outward. Therefore, this will be your electric field direction also. Okay. Therefore, this is ds is a small area element. And what is the direction? Therefore, area vector will be denoted by, what is the direction is given by unit vector n. And electric field intensity will be definitely, it is radially outward. Okay, because at this point, if I keep a unit positive charge, it will be moving in this direction. It will be moving in this direction. Therefore, that is E. So, E and ds vector, area vector, are in the same direction now. I think you are able to understand, right? Therefore, now I am going to apply Gauss theorem. Integral of, okay, E dot ds, that is equal to integral, okay, E, okay, dot ds is, what is that? N ds. Okay. Therefore, and that is nothing but, let Q be the total charge here. Q is a charge. And also, because the charges are uniformly distributed, I can even, what is that, represent this by, let sigma be the surface charge density. I am sigma be the surface charge density on the sphere, of the sphere. Okay, therefore Q is the total charge. Okay, therefore how can I represent Q? Therefore Q, that is nothing but surface charge density into what, the surface area of the charged sphere, that is 4 pi r squared. Is it clear? So this is why sigma is surface charge density, means charge per unit surface area. Therefore, Q is the total charge on it. Therefore, what is that? Sigma into 4 pi r squared. Capital R. Capital R is the radius of the sphere. That is charged shell. Okay. Therefore, that is equal to Q by epsilon naught. Q by epsilon naught. Are you following? Therefore, you can say this by E dot n ds both in the same direction. Therefore, that is nothing but E, okay, if I take, it is E ds. Okay, why? Because E, it is nothing but E ds cos theta, na? E ds cos theta. Therefore, that is nothing but E ds. I think there is no need for to tell by E dot n. That is nothing but n ds means E ds cos 0. Therefore, you will be getting E ds. That way, slightly I have written E integral, surface integral ds. That is nothing but Q by epsilon naught. Hope you are following. Okay. Therefore, what is ds here? E. What is this is ds. Therefore, what will be the total surface area? Total surface area of the Gaussian surface will be 4 pi r squared. Surface area of the charged shell is 4 pi capital R squared. Surface area of the Gaussian surface means it is 4 pi small r squared. I think small r is the distance. Therefore, that is nothing but Q by epsilon naught. Q by epsilon naught. Therefore, what is your E here? E, that is equal to Q by 4 pi epsilon naught r squared. Correct? This is the expression for electric field, I think. Okay, therefore, this shows that this expression shows that the charge is uniformly, all the charges Q are uniformly distributed on the shell. But here you are getting the electric field as E is equal to Q divided by 4 pi epsilon r square. This is very much equivalent to charge, what is the electric field due to a point charge Q, correct? The electric field intensity due to a point charge is nothing but Q by 4 pi epsilon naught r squared. Therefore, in this case, the charged spherical shell acts Okay, as if the whole charge, all the charges are concentrated at the center of the shell. Okay, when the point of interest is outside the, what is that, shell, P. When we take the, for points outside the shell, for all the points where you have to find out the intensity, if you take it outside the shell, then the, how the shell behaves, the charge, the shell behaves as if whole charge is concentrated at the center. Therefore, all the charges are concentrated at the center. That is why you are getting, what is it, Q divided by 4 pi epsilon naught r square. Actually, it is spreaded. All the charges spreaded in the, on the surface of the shell. But when the point P is taken outside the charge shell behaves as if all the charges are concentrated at the center. That is why you have got this expression as E is equal to Q by 4 pi epsilon naught r squared. Hope, okay, I think once again I'll repeat this. For points outside the spherical shell, the field due to the uniformly charged shell is as if the entire charge of the shell is concentrated at the center of the shell. At the center of the shell. Are you following? Right. Now, I want to give the same expression in terms of surface charge density. Surface charge density. Therefore, this can be written as E, that is equal to, what is Q? Q is equal to sigma into 4 pi r square. Correct? Okay. Divided by 4 pi epsilon naught r square. Are you following? Therefore, you will be getting 4 pi will get cancelled. Therefore, you will be getting here sigma r squared by r squared. Sigma capital R squared divided by small r squared. Okay, so you are getting one in with respect to total charge and one expression with respect to the surface charge density of the spherical spherical shell. Is it clear? Okay, right. Next one. So we are going for the next part is here. Okay, now next one. For points outside the for point lying, okay, for point what is it, lying on the cell, on the surface of the shell. Okay, therefore now you see here, what is that? This is okay, now I have the, this is my, okay, and what is the radius here is r. Okay, now my point of interest here is lying on the surface. Here charges are distributed. This is the charge. Okay, therefore my point of interest P is lying on the shell itself, on the therefore this is my point of interest. Okay, now you tell what to do here. Here r, this is the distance here, distance of the point is r. Here r is equal to r. The previous case r is more than small r is more than capital R, that is r is the radius of the shell, right? Now therefore Gaussian surface, there is no need to draw a separate Gaussian surface here because the shell itself is a Gaussian surface. Okay, why? My point of interest is lying on the shell. Okay, therefore now take a small ds. Okay, therefore what will be the direction here? The direction will be, direction of E here will be in this direction, and ds unit vector will be in this direction. Okay, therefore I will get here r is equal to r. Therefore you can have E dot ds, okay, that is equal to E dot n ds, okay, and that is equal to, okay, that is equal to, what is that? E ds cos theta cos 0. Therefore you will be getting E ds, okay. Therefore now it is E ds, okay, and that is nothing but, what is according to Gauss theorem is, what is q by epsilon naught, correct? Therefore you will be getting E ds is, what is ds here? 4 pi capital R squared, na? Because the Gaussian surface is nothing by having the same radius as the shell, okay, that is equal to q by epsilon naught. Therefore E, that is equal to q divided by 4 pi epsilon naught r squared. Therefore this is the expression. Okay, with respect to what? With respect to the charge q. And now I want to give the expression with respect to surface charge density. Therefore you can even write E, that is equal to surface charge density is nothing but, what is that here? Surface charge density is, okay, surface charge density here is yeah, sigma into 4 pi r square. Sigma into 4 pi r squared is nothing but what is that? Total charge q, is it? Therefore divided by, okay, 4 pi epsilon naught r squared. Okay, therefore everything, the 4 pi r squared will go. Therefore you will be getting sigma by epsilon naught. Sigma by epsilon naught. Therefore the value for E here is sigma by epsilon naught. Okay, this is the other expression. Okay, right. Hope you are following. Okay, so now next one. What is the next one? Let's see. We are going to see wait. The next one is when. Let me write here itself. Okay, because the version is new version, no, that is why there is a slight, okay, yeah. Now for points outside the okay, let me have, wait, this is okay. Now for point inside the shell. Okay, therefore let me have, this is my, okay, now I have the point here, this is capital R. My point of interest is here, the inside. Okay, therefore the charges here are uniformly distributed. Okay, and therefore now if I draw a Gaussian surface, see, this will be the Gaussian surface. Okay, therefore what is the this is a point, therefore what is the distance of the point? This is P. Okay, this is your R, this is your R, correct? Therefore, once again, this is the point, this is R. Okay, therefore, now sphere is slightly distorted sphere anyhow. So, kindly see, it is not a proper sphere now. Anyhow, I think this is okay. Okay, slightly better. Now, therefore, now you tell me what is according to by using Gauss theorem. Okay, integral of E dot ds that is equal to, what is that, q by epsilon naught, correct? But here it is nothing but E into 4 pi r square, correct? E into, because E ds, everything here ds I am taking here, this is ds, okay? Therefore ds will be in the ds and E electric field all are in the same direction. Therefore E into 4 pi r square, that is equal to total charge enclosed by the surface, correct? What is the total charge enclosed by the Gaussian surface? It is 0. No, it is not. Enclosing is q, that is equal to 0, because what is, this is our Gaussian surface. See, the Gaussian surface is this one. Are you following? Let me have pink. So this is our Gaussian surface, okay? And this Gaussian surface is not enclosing any charge, because my charge shell is outside the Gaussian surface. Therefore, what is that? That is q by epsilon naught, that is equal to 0. Therefore, what is E? E that is equal to 0. E that is equal to 0 for points inside the shell, electric field that is equal to 0. Are you following? Okay. Therefore, E is equal to 0. Therefore, you can say when R is, okay, less than capital R. What is R? This is your R, radius of the shell, है? This is your R. Therefore, your the distance of the point concerned is less than the radius of the shell. Then you can say that, what is that? E that is equal to 0. Okay, right. Therefore, now I am going to plot a graph. Okay, what graph? See, see, variation of electric field intensity, okay, with the distance from the center of the uniformly charged spherical shell. Okay, so how to? Now let me well, how to see? Okay, and this is okay, x-axis, y-axis, okay. This is your E, okay, and this is the distance of the point from the center, distance from center, that is smaller, distance of the point concerned from the center, right? Now, how to plot? See, if I am taking two different, what is that, distances, for, see, distances means what is that? See, here first distance here R is, distance is less than R. Okay, when the, which means the point is inside the spherical shell. That time, till that, what is that? There will not be any electric field, right? Next one is, and it is going up to, okay, this point. This is nothing but, okay, R is equal to R. When r is equal to r, see, I think we have seen, once again I'll, for r, what is that, more than r, the point is lying outside the shell. Okay, therefore your answer, what is E? E, that is equal to, okay, sigma r squared by r squared, correct? And when r, that is equal to r, okay, what is E? E is equal to, okay, sigma by r squared by r squared, epsilon naught, sorry, by epsilon naught. Okay, but here it is sigma r is equal to r means sigma by epsilon naught. When r, that is less than r, then E, that is equal to 0. So all the three you are going to what is it, implement here, that is here while plotting the graph. So r less than r means electric field will be equal to 0, and here this is a point r more, therefore here this is the maximum possible. E, here it is nothing but maximum possible value of, what is that, electric field intensity. Therefore there will be, it will shoot up, it will be maximum. Okay, therefore I write this one as E max. Okay, after that, this point r, that is, this is r equal to r now. After that it will be r more than r, correct? Therefore how it will be? It will be here, what is that? The shape will be like this. Why here? E is actually inversely proportional to r squared. E is inversely proportional to r squared. Is it clear? Therefore, r less than r means 0. R equal to r means it is maximum value, that is sigma by, what is that, epsilon naught. Okay, and when r is more than, small r is more than capital R, see r, small r is more than capital R, okay, then E is inversely proportional to, what is a small r squared. Here capital R is the radius of the shell and small r is the distance of the point from the center of the charged shell. Okay, I think we are able to understand this. Okay, fine, right. Now